Hi, so my name's Jim. I'm CEO of Hopsworks and Associate Professor at KTH in Stockholm. I'm going to talk about how we get data from the Lakehouse to Python using, in particular, Apache Arrow. And I'm going to start by talking about data processing at scale. And there's different scales. You can see I have a diagram here with different data processing technologies. So we have smaller scale on the left-hand side. So pandas might be considered a small scale data processing tool, and polars can scale to larger volumes of data. And typically when people have very large volumes of data, they move to using tools like Apache Spark, or maybe a data warehouse in the cloud and DBT, so maybe BigQuery or Snowflake. These tools can handle, they can scale to process terabytes or petabytes of data as batch applications. And of course you have real-time. We're not going to cover real-time today. You have tools like BiteWax for Python, and then when you move to scale, you might use to Flink or Beam or Spark. So what's interesting here, particularly for the Python community, is that you can see we've got Python tools on the left-hand side, and everything on the right is considered not Python. So we think of distributed data processing on the right-hand side and single host processing on the left. But what we see now with increasingly large compute, so you can get virtual machines with 32, 64 CPUs and a lot of memory, so hundreds of gigabytes of memory, there's an increasing possibility for doing data processing at reasonable scale. So what we can see here is that, the data warehouses say, well, we do both small scale and large scale, and Python is the provision of small scale, but Python does this kind of little area here. This is what we might call single machine workloads. And as single machines are getting larger and larger, an increasingly large volume of workloads become possible in Python. And that hopefully will make it easier for people to do data processing in Python at reasonable scale. Now, one of the challenges with this is that a lot of the enterprise data is increasingly be stored in what is called the Lakehouse. So Lakehouse is really columnar data stored in object storage using a table format like Delta Lake, Apache Hudi, or Apache Iceberg. They're the three dominant table formats. So what those table formats give to Apache Parquet files are ACID updates. They give you incremental updates. You can delete data. So you can be compliant with a lot of enterprise requirements. And they also provide indexing as well, so that you can get faster access to your data. So this is great, and they're becoming widely adopted. So large volumes of enterprise data are being stored in the Lakehouse, and the tools that are being used to write the data, like Spark or Flink, are obviously very scalable. And the first users of the Lakehouse are primarily business intelligence tools. So we have query engines that scale to massive volumes. So everything from Snowflake using Iceberg to Databricks using Delta Lake to Trino using Hudi. We have all these different query engines that can access the data. So how does Python get the data from the Lakehouse? Well, most of the existing interfaces for Python to the Lakehouse are via JDBC or ODBC services. So these kind of servers are a bottleneck because the data in the Lakehouse is stored in columnar format, and these are row-oriented format. So the data will have to be pivoted from column-oriented to row-oriented and back again. So the question is can we get to the data in the Lakehouse more efficiently and faster from Python so that we can work with this data in pandas or polars? And we'll talk about that in the course of this talk. And we're going to talk in particular about using Apache Arrow and a query engine, DuckDB, to get faster access to Lakehouse data for Python clients. So if business intelligence is primarily the main consumer of data from the Lakehouse at the moment, where's the burning need for Lakehouse data in Python workloads? So we don't have that many Python workloads in business intelligence, but we do have them in machine learning. So machine learning, as we know, is about building machine learning systems, and a machine learning system will take your raw data on the left here. We'll be able to create features from it. When we have a feature store, we typically have this particular architecture to make up a machine learning system. We have a feature pipeline which will take your data, it'll transform it into features and labels. We call that a feature pipeline. So its input is data, potentially from the Lakehouse. It'll create features and we'll store them in the feature store. And those features and labels can then be used to train models. So the model will be stored in a model registry, And then finally, we'll have an inference pipeline, which will take a trained model and some new feature data and make predictions. That could be an online inference pipeline or a batch inference pipeline. And what the feature store does is it gives you access to this data that we're going to use, the feature data and the labels that we're going to use to train and make predictions with. It gives you two APIs. One is a lakehouse. So the data is typically stored in a columnar store like a lakehouse. And that's the very large volumes of historical data. But the feature store also gives you very fast access to the latest feature values for your online applications. And that's often stored in what we call a row-oriented database. So row-oriented databases are optimized for primary key lookups, and columnar databases like the Lakehouse is optimized for queries such as workloads such as aggregations and reading large volumes of data at relatively low cost. So this is where we have the need for Python access to the Lakehouse data, because feature stores typically store their data, their offline data or historical feature data in a Lakehouse. So our Python clients will need to read that data. And if you're going to train a model, and let's say you're using scikit-learn, you're probably going to want to use some client like pandas to read your data and then train your model in scikit-learn or PyTorch or TensorFlow. And similarly, when you're doing batch inference, you may do batch inference in PySpark, but you may also do batch inference in Python. If you're doing batch inference in Python, you want to be able to read large volumes of data from your lakehouse, so pre-computed features to make predictions on at quite high performance. So, as I mentioned earlier, existing feature stores typically provide an ODBC or JDBC style API to retrieve that data from the tables that make up the lakehouse. So we call them feature groups, the tables that make up our features. And this, as we know, is a bottleneck. So what we've done in Hopsworks is, Hopsworks is a feature store. It was the first feature store for machine learning, first open source feature store, I should say, and the first enterprise feature store. We've seen this problem from quite a way back. Feature stores were originally Spark-based platforms, including Hopsworks, which still supports Spark as a query service. But what we did was we built a new feature query service around DuckDB using Arrow as the transport protocol from the data stored in the Lakehouse files to the training pipelines and batch inference pipelines, the clients that read that data. And the very interesting result of this is, of course, a huge improvement in performance. Effectively, what was previously go grab a cup of coffee or go grab some lunch before your training data is ready has now become an interactive process. You can read millions of rows of data in seconds. So I'm going to talk about the technologies here. We've got Apache Arrow at the start. So Apache Arrow is an in-memory data format. It's also an over-the-network format. You can send Arrow data over the network as the transport protocol, or the protocol of messages that are being sent over the network. It's organized in a columnar layout, which is, of course, optimized for analytics. So you can read data from Parquet files directly into Apache Arrow files without any pivoting of the data from row to column-oriented format. And as such, it's also used as an exchange between different frameworks. So Spark has used, PySpark has used Arrow for quite a while, so that executors can read in Python, can read data in Arrow and perform UDFs and pandas on that data without copying the data from the JVM to Python and back. And that's been very efficient for them. And we're now seeing it more widely used within the Python ecosystem for example, moving data between pandas, polars, and DuckDB. There's no need to copy the data anymore. So from pandas 2.0, Arrow is the backing engine for pandas, and now we can do zero copy reads between these different frameworks. So Arrow has huge potential for enabling the data to being shared between different data processing engines and to be transported efficiently from the Lakehouse to the client. Now, there is an existing RPC protocol called Arrow Flight for defining how to transfer Arrow data from a service to clients. And we built on this particular service as a way of transferring data from the Lakehouse. So you have a server, so we've developed a server, and that server can read up Arrow tables from the Lakehouse and transfer those Arrow tables to, for example, a Pandas client that can then use that data in a training pipeline to train a model. Now, we didn't do this without doing our research first. So we looked at some of the benchmarks that are out there, and there's some very interesting ones. This is from last year, 2022, where they showed a 30x improvement over JDBC and ODBC for reading from the New York taxi data set. And this was done by Dremio. And we can see that here blue is the Arrow flight time taken to read the data from a columnar format to another columnar client. So in the case of ODBC, they obviously need to do this pivoting from the columnar to row-oriented and back again, but you also have to serialize your data and deserialize your data as well, which also costs a lot of CPU time. So the JDBC, ODBC, we can see visually we're going from this server where we've got columnar data to the protocol, which is row-oriented, and back to the client, which is column-oriented. And that just takes a lot of CPU time now, particularly with increasing data volumes. That becomes less and less practical. So I assume we're going to see lots more of our data warehouses moving towards Arrow as a native protocol where clients can read data directly in Arrow. There is actually a driver now called ADBC, which is an Arrow database driver supported by DuckDB, where you can read Arrow data from clients, similar to JDBC. So we didn't build on that. We built on Arrow Flight, and we used DuckDB as the query engine. Now, DuckDB is a lightweight in-process analytical database management system. You can pip install DuckDB in your Jupyter notebook. You can have an ETL pipeline that can use DuckDB instance to do data engineering. And what we did is we had an Arrow Flight server using DuckDB to perform the queries on our feature store. Now, these are all possible ways of using DuckDB. There are many others. And DuckDB in particular, we have a particular workload in feature stores related to creating training data, which we've seen in Spark is quite challenging. So it's called a point-in-time correct join. What it means is basically you have your label or target data in some table with timestamps for the observations of those label data, and we want to join in features from other tables. And those other tables is often time series data, and we want to find the feature value at the correct point in time. Now, DuckDB, when we want to perform the joins across many different tables, you can see this join benchmark released recently by DuckDB. We can see its performance over Spark, which was our previous engine, is quite significant, from 8 seconds for this join benchmark to 129 seconds in Spark. Now, Spark does have a startup time and so on. And we did quite a lot of work on Spark. So we've actually changed the join, implemented our own join algorithm for Spark to improve the performance of these point-in-time correct joins. But still, we noticed that the performance wasn't as good as we wanted to have an interactive experience for Python developers, able to read this data interactively from the Lakehouse. So what we did was we developed this service we're calling the HopSworks Feature Query Service, powered by DuckDB and Arrow Flight. And the goals of this service is to make an easy-to-use, secure, lightweight Python client with fast access to feature store data, which is ultimately stored in the Lakehouse, using, in particular, temporal joins. So I call this a point-in-time correct join. It's a temporal join. You're trying to join features from different tables that are updated at different cadences. So you're not doing an equality join where you're saying, here's the value of my label at this point in time, give me exactly the features at this point in time, because those timestamps are never lined up. Each table will be updated its own cadences. So we need to do a temporal join. We need to find the closest timestamp for this feature at this point in time, but earlier. We don't want later, otherwise we would have what we call data leakage. So this is what the service looks like. We have a client at the top here, and this is Python World, and we're trying to interface Python World efficiently with Lakehouse World at the bottom. So the Lakehouse World at the bottom is ultimately going to be our Lakehouse tables, which in our case we're using Apache Hoodie and Parquet files as the Lakehouse. So that's stored on S3 ultimately, and we have a caching layer called HopsFS on top of that. So our service, the HopSworks Feature Query Service, has DuckDB internally. It's able to read up the data from the Apache Hoodie tables, these Parquet files, as Arrow tables. So DuckDB can read up that data natively, and then it might need to perform temporal joins across the different tables. And it can do that on the Arrow data directly, and it sends the Arrow data direct back to the client. Now we notice that the client here sends a query in here. I'll show in a minute that we're not sending SQL as the query directly, so HopSworks abstracts that away from you, so you don't have to write these complex temporal joins. And then finally, when the data arrives at the Arrow Flight client with zero copy, it can be imported into the Pandas DataFrame. Now, we did a little bit more work than just this, which is a query service for the native data stored in Hopsworks, because Hopsworks supports external tables. So you can have as your offline store BigQuery or Snowflake or Redshift, which are our data warehouses. So what we added to our external query service was the ability to join across features from, for example, Snowflake, where your labels might be in Hopsworks, and we can do this kind of federated query. So the way that that works internally is that we push the queries down to the external tables, and we retrieve the data as Arrow data, so Arrow tables, and then DuckDB can perform the joins internally, these temporal joins internally. Now, DuckDB is an in-process server, so if you run out of memory, so one of the recent versions, it will spill to disk, but when it spills to disk, performance will suffer. So typically, this service is optimized for queries that return, that fit in memory, the amount of memory you allocate to this feature query service. Slightly more in spilling to disk a bit is not too bad, but if it's much larger, then you would typically move to Spark. So if you were to create, say, let's say many tens of terabytes of training data, typically you would use our Spark engine. But if you're creating training data on files that's not necessarily huge, maybe it's only gigabytes, you can do this also with our feature query service. So what DuckDB will do is it will create, for example, Parquet files as training data, and it'll store them using whatever connector you use to an S3 bucket or GCS bucket or HopsFS or wherever you're going to store your training data. So this is the query, the temporal join that I talked about for creating training data. It's quite complex. So I have three tables here. I have a table in the top left-hand corner called trip duration. And we can see we have trip seconds as our labels. This is the legend down here in the bottom. This is the thing we're going to try and predict in a machine learning model. And to do that, we need features. So I have the total amount spent, which might be a useful feature for predicting trip time, because if I spend more, it's probably a longer trip. And we have trip miles, which may be available to you, but it's it's quite a good feature. It may not be available to you beforehand. So you can see there's a null here. Because sometimes we won't know, of course, before a trip has started, how long the trip would take. And then we have the number of days until your credit card expires. And I'm not sure if that's a great feature for this particular model, but it's included here. Now, there are other columns in here. So our tables have a primary key. You can see we also have an event time column telling us when this feature had this particular value. And we have a foreign key here, pay ID, pointing to this other pay ID column here. And credit card number is another foreign key. So the way in which the training data is created is it's actually a left join. We start at our label table here, and then we join in features from the trip payment table and from the payment details tables as features. And we're doing a left join, but it's also an as of join. So it's going to take, if we take, for example, row 3 here, the 14th of January, 2021, it's going to take the feature value which is closest to it, but not later. So it's going to be the closest, but the same day or earlier, which is this row here. And this row here has a trip miles value of null. Now, it's a left join, so we're still going to include that in our training data at the bottom. And then we're pulling in another feature. This is 100 expiry days using a nested left join. So we're going to push this down to our database. Now, DuckDB supports a left as of join, which is great. It means that the SQL to create this is relatively straightforward. And what we get out of it is our training data down here. We have our 3 input features, we have our label column, and it's okay to have a null here because later on in our training pipeline, our inference pipeline will impute that value, or we'll set it to being some other value. So if I'm to do this if I don't have a feature store and I want to create this type of training data from a data warehouse, this is showing some code from BigQuery. What you end up is writing very complex SQL queries. And one of the reasons why you end up writing complex queries, this is not a temporal join, by the way, in case you're curious. It's just showing a large amount of SQL, and it's embedded as a string in your Python client. And how you access that data from BigQuery, for example, is that you pass this string down, it executes it as a job, creates a temporary table, and then it reads the table into a data frame in Pandas. And this is the bottleneck you have at the moment. Now, the complex point, if you say, well, I'm not going to use a feature store, I'm going to write this code myself because I've only got batch jobs, and then it's pretty straightforward to do this temporal join, this temporal left join. most data warehouses don't support left as of joins today. They don't, excuse me. And then you end up writing very complex windowed operations, which are extremely challenging to do. So if you don't want to go this route and write very complex SQL, this is how you would write this code in HopsWorks. So in HopsWorks, you would log into the feature store. We get a reference to our 3 different tables. We call them feature groups: trip duration, trip payment, and payment details. And then we select the features that we want to include in our model. So we create something called a feature view. This is the interface of the model, the features and the labels that we have in our model. So we select all of the features in the first feature group, join them with all the features in the second, and join them with the features in the third feature group. And then we create our feature view with the name taxi, and the column that we are using as the target or label is trip time. And this is our selection of features here. So with this feature view, we can easily create training test data split into our features and our labels. And there's DataFrames, and then you can call model.fit on the training set of features and labels. And then you can evaluate your model by seeing its performance on the test set of features. So this is YPRED, and then compare the performance of the predictions using the Y test labels, which are the outcomes, and the predictions. And then this model you can register in the model registry, such as HopsWorks. So the complexity of writing all the SQL is kind of hidden for you, but we're pushing it down. But most importantly, the performance of this is really good. So let's have a look at some of the performance numbers. And with the proviso that these experiments were performed in September 2023, things are moving very fast in the space, and I expect that the data warehouses will add support for Arrow data in the near future. So these experiments were performed on the New York taxi dataset. It's a well-known data set. And what we're trying to do is firstly just read training data from the feature store into Pandas DataFrames. So that's something that you commonly would do in a training pipeline. So we have a client over here in Pandas that's going to read 5, 10, 20, and 50 million rows. And what we're counting is the number of rows per second that's read from our query engine. So here we can see HopsWorks is getting somewhere between 2 and 3 million rows per second. SageMaker is not doing so great. We can see that the Vertex is getting better at slightly higher volumes, and Databricks has problems when you call 2 pandas. We had difficulties in getting it to work at 20 and 50 million rows. So this is basically the difference between using Arrow as your transport protocol, but also DuckDB as our point-in-time join engine. Now, we repeated this for creating training data, which is another thing you might do in your training pipeline. You'll say, well, I don't want the data back as Pandas DataFrames. I'd like to have it as Parquet files, and I'll train my model with that. And again, we saw a large improvement in performance for HopsWorks compared to the other feature stores. And these feature stores are backed by SageMaker is backed by Athena, Vertex is BigQuery, and Databricks has its own Spark engine. So I can show this briefly. We can have a quick look at this in action in HopsWorks. I think we have a couple of minutes. So I had the Chicago taxi data set. It's a slightly different one to the New York one. And I imported 114 million rows here into this feature group. So this is a table of features. We can see there's a bunch of data there. We can get a preview of the data. This is what it looks like. And basically, I can spin up a notebook and start reading that data. So one of the challenges with feature stores was that it wasn't really interactive until we released this service. It would take quite a while to get your data. So here I have I'm logging into HopsWorks, and I'm going to read some data from this Chicago taxis feature group, and I get a reference to it. I'm just counting the time it takes here, and it's quite big. There's 111 million rows, so I'm not going to read all the data. I'll just read the data after 2022, and you can see it just said, okay, reading data from HopsWorks using Arrowflight, and this is all running on a single server, I should add. So this isn't like scaled out to have a lot of CPUs running on it, but I've read back, what's this? Just over 1.3 million rows. So it's pretty interactive, and it's a nice way of getting your data quickly. That's it. And with that, then I'd like to conclude. We get a feeling for the performance benefits that we get when we use Arrow Flight in particular, or Arrow protocol, to transfer data from the Lakehouse to Python clients. And we get a great boost in terms of this temporal join with DuckDB compared to using Spark. And I think what is really important about this is that if you can reduce the time it takes to get data, feature data to data scientists, they can work in a more data-centric AI manner. You can easily do experiments with different sets of features, different ranges of featured values. You can do not just the random splits I showed you, time series splits, and use different ranges of data. And it makes your way of working more interactive with a feature store, and it makes it more natural for Python developers. And what this gives you the ability to think of is that the feature store can be kind of like a network drive for your data frames. It's easy to just ingest new data, keep writing new data. It manages the incremental data sets for you, and then you can read that data at network line speed. So it's not going to slow you down compared to having to previously maybe store your data on your laptop and do all your work there before you go back to the cloud to get to do more work. So that concludes the talk, and I'd like to thank everyone at this point. And if there are any questions, we can take them in the chat.
Yeah, thanks so much, Jim. That was awesome. And as you mentioned, there's nothing in the chat now. So if anyone currently viewing has any questions, we got 3 minutes to cover some of those. So happy to dive in. If not, let's give it a minute. Awesome. We're waiting for some of those. Again, just want to say that if anything does come up or if anything sparks your interest, we can continue this conversation in Discord. You'll actually be able to find a link available in the reception area, and then you'll also be able to access this recording. And I am pretty sure that these recordings come out as soon as the session is closed. So if you missed anything or you want to go back, I think that within the next few minutes you should be able to do so.
There is a question from Emily there. Just is the code language used in Hopsworks Python? So Hopsworks has APIs. There's a Python API. You can also use Spark, Flink, and there's a Java API as well. So you can use all those different ways of interacting with the platform. And there's another question from Ross popped up. I haven't used DuckDB. Does it support parallel writes and reads? Sometimes embedded databases don't. It does, Ross. So there's different connectors. We're using the FS-spec connector. There's also an S3 connector, which does parallel reads. So it's because, again, DuckDB is multi-threaded. So Python, we have this, global interpreter lock that is a scalable bottleneck. But if you use DuckDB to read, it can use as many cores as you give it. And for example, with the S3 connector, it'll read from different. If you have a Parquet data set with many files, it can read many of those files in parallel. And it makes a huge difference in terms of performance. And it does that also with the FS-spec API that we're using to HopsFS. I will upload the slides into the Discord. Thanks, everyone.